Hello, everybody. Welcome back to another video. And in this video, we're going to be taking a look at a question from the IB Chemistry paper to HL from the May 2016 batch. Now, this is question number 3, and it asks us, the reaction between hydrogen and nitrogen monoxide is thought to proceed by the mechanism shown below. First part of the question, state the equation for the overall reaction. Now, such questions, again, very standard textbook questions, and you will see them in almost every single exam that you come across. Now, how do you do this? How do you state the overall reaction based off these a bunch of these three equations? Because you have this fast equilibrium, slow reaction, fast reaction. You've given three reactions. How do you state the overall reaction for this entire process? Now, what you have to do is very, very simple. The first thing you need to do is you need to cancel out the substances that come on both sides of an equation. So what I mean by that is, let's take a look at this. In the first reaction, we see that N2O2 is being formed, and we see that in the very next reaction, it is also being used up. That means that this is an intermediate substance. That means it is formed and immediately used up. That's why we don't consider, or we don't count these, or we don't mention this substance in the overall reaction. So we have to cancel them out. These are not going to be part of our overall reaction. Let's see if we have any other substances like that, which get produced in one reaction and get used up in the next. Do we have any other substance? Yes, we do. N2O gets produced in the second reaction and it gets used up in third. So we cancel these out as well. These are called intermediates. These are out. Any other substance? Any other substance? Nope. We can see no other substance. Now, you've canceled these out. What do you do with the rest? What do you do with 2NO, H2, H2, and then you have the products as H2O, H2O, and N2? What do you do with this? Well, it's really simple. All the substances that are on the products, that are on the reactant side over here, U2N2, 2NO, H2, H2, and all the substances that are being produced on the products side, like N2, H2O, H2O, well, you just write it as it is. You combine them. So it'll basically be 2NO, because we have 2NO, plus 2H2, because it's 1H2 and 2H2, gives us 2H2O, because you can see that there are two H2Os being produced, 1 and 2. But we don't cancel these out. We don't cancel these two H2Os out because they're on the same side. They're both are being produced. We only cancel those substances which are being produced and which are being used immediately. And it's the same case for H2 as well. We don't cancel H2 out because in both cases they're being used. They're not being produced and used. So produced and used means cancelled. N2O was produced and it has been used. Same case with N2O2. It was being produced and then it was used. So you cancel them out. Anyways, so 2H2O plus N2, which is being produced as well in the final reaction over here. That is our overall reaction. That's it. Just remember to cancel out the substances which appear on both the reactant side and the product side. That's what you have to cancel. This is our overall reaction. That's how easy it is. There you go, one mark in the bag. Let me just move this thing up. Now, moving on to the next question. Deduce the rate expression consistent with this mechanism. So now, really, what these three equations signify, what they signify is really a breakdown of what happens in this equation. Now, this is the overall reaction, but even behind the overall reaction, there are specific steps that take place, and these are the specific steps that happen. The overall reaction doesn't give us the full story. It just shows us what was used and what is produced. It gives us the net gain, and it tells us the net use of substances and the net gain of substances. Whereas these three equations tells us everything that has been produced in the middle, in the end, in the beginning. It gives us the whole picture, the whole story, right? And if we want to determine what the rate expression is, we need to look at the whole story. Just looking at the overall reaction is not going to give us a fairly accurate representation of the rate expression. So if you want to get the rate expression, we need to look at the whole picture. And what is a rate expression? Well, a rate expression is something that uses the concentration of the reactants that are taking place in a specific reaction like this, and it uses another number called the rate constant K. You would have heard of it, and it gives us the rate of that overall reaction. Now, this is basically the template for what a rate expression looks like. So rate expression is K, which is a constant, times the concentration of substance A raised to the power of whatever its coefficient is. If its coefficient is 2, it is raised to the power of 2. For example, like NO, it would be NO squared. Whereas if it's something like, whereas if there's just no coefficient, it's raised to the power of nothing times the concentration of substance B. There could be substance C, D, E, whatever, right? We could keep going. This is the general template for rate expression. Now, how do you calculate the rate expression based off these three equations? How do you even do that, right? For the rate expression, all you need to know is that the rate expression is going to be given to us by the slow reaction. We use the slow reaction as a benchmark to calculate the rate expression. And in most cases, this would be true. However, in this question, it's a bit of a special case because if you look at it, there's also a fast equilibrium occurring right before the slow reaction. And in such cases where there is another reaction occurring before the slow reaction, we need to also take into account the fast equilibrium or the fast reaction. We need to take both into account. However, imagine if this wasn't there. Imagine if this didn't exist. Just imagine. If this didn't exist, you would only use the slow reaction to calculate the rate expression. So if you ignored this, if you just ignored this, the rate expression would then be K times the concentration of substance A, which is N2O2, times the concentration of substance B, which is H2. This is, we take into account the reactants. We don't look at the products. This would be the rate expression if the fast equilibrium didn't exist, but it does exist. So we need to take that into account. We need to take the fast equilibrium into account as well. And you may be asking, why is the slow reaction the benchmark for the rate expression? Why don't we use a fast equilibrium? Well, let me show you why. Imagine you have a beaker, right? Imagine you have a beaker. Let me just draw this down here, okay? You have a beaker. There is water inside the beaker, okay? And you have a funnel. You have funnel number one. There's a funnel and you pouring water through it. But then this funnel is attached to another funnel on top. However, this funnel on top is a bit smaller. It's not as big as the other funnel. So it's attached to this. This is attached to the beaker. But this funnel isn't as big as the funnel at the bottom. So this is funnel A, this is funnel B. And on top of funnel B, let me just move this up. Sorry, you just give me a second. Oops, I'll just erase it. It's much easier that way. Yeah. So imagine on top of funnel B, you have another funnel. This funnel is as big as funnel A, and we can call this funnel C. So imagine if you pour water into funnel C. We're pouring water. Okay, this is water. It's coming into funnel C. It's going down into funnel B. Now, even though funnel C is just as big as funnel A, you cannot expect the same amount of water that you pour into funnel C to immediately reach funnel A, because the middle step, this over here, funnel B, has a lower quantity, or it has a less quantity to handle water. So this funnel B right here is kind of controlling how fast the water is flowing, because it is determining the maximum speed of the flow of water. It's limiting it. So therefore, it is also determining how fast it can go. If this funnel, if supposing this funnel B, if I increase its size, if I made it much bigger, then there wouldn't really be a debate. However, funnel B is much smaller than funnel C and funnel A. So it determines how much water can pass through at a specific amount of time. It is the limiting, you can think of it like the limiting equipment in this. And very similarly, in this reaction as well, you have a limiting factor, or you have a step that determines how fast a reaction can go. And that is your slow reaction. And the slow reaction is the equivalent to funnel B in this case. It is the slow one. It is the one that determines how it's going to set pace to the reaction, basically. You can imagine it like that. But, but even though the reaction speed depends, or or how fast the reaction can go depends on the size of funnel B, it also depends on funnel C, because imagine if I stop pouring water in this, well, then what happens? Well, less water is going to pour through, or eventually it'll stop. So funnel C then also plays a vital role in facilitating the flow of water through the funnels, right? That is just an analogy for you to think about. That I'm giving you an example, and hopefully you've understood what I mean by this. So funnel A is funnel A, it doesn't really matter, right? Unless I make funnel A smaller than funnel B and C, it's not going to really affect how fast the water is flowing through. For now, in this example, really the only parameters to determine how fast the water is going to flow through is how much I pour through funnel C and how much water can pass through the limited size of funnel B. So how is this relevant to this question, and how are we going to use the fast equilibrium and the slow reaction to determine the rate expression? Well, the very first thing you need to do is that you can't use two equations. You need to combine the fast equilibrium and the slow reaction to gain an overall reaction. You can't use two equations to create one rate expression. It doesn't work like that. So you need to combine these two equations, and you combine them by exactly how I showed you earlier. You cancel out the intermediates, you cancel out the substances that are being produced and that are being used. So you cancel out N2O2. There's nothing else to cancel. So the overall reaction is just going to be 2NO plus H2 gives us N2O plus H2O. This is the reaction that is going to help us create our rate expression. And like I said, just substitute the values into A and B. So rate expression is going to be, I'll just write this at the top. Rate expression is going to be equal to K, which is the constant. Never forget to write the constant. Even if you don't know what it is, always write the constant. K times the concentration of if I'm not wrong, this is nitrogen monoxide. And since the coefficient is 2, we square it. Times the concentration of H2. And H2 doesn't have a coefficient, which basically means there is a 1 there. So we don't have to write that. But if you really want to, you can just write to the power of 1. It really doesn't make a difference. That's it. That is how you reduce the rate expression in such a question. And remember, you only include when you calculating the overall expression to calculate the rate expression. Now this is much different to this. If you notice, the equation that we calculated over here is an overall reaction. This is the rate determining reaction. This reaction determines, or it gives us a rate expression. So there's a big difference between these two. So when you are creating the equation which will help us determine or get our rate expression, you only consider the slow reaction and any reaction that comes before the slow reaction. And in this case, we have only had one reaction that comes before the slow reaction, which is the fast equilibrium. That is it. That's it for this video. I hope that you have understood this concept. If you have any questions regarding this concept or any other concept, please feel free to reach out to me on my social media, put it down in the comments below, or send me an email. I'll be more than happy to help you. Thank you so much for watching. I will see you in another video with another question. Take care and goodbye.